Hi everyone, my name is Derek Snyder and I'm a product manager for LabVIEW. I'd like to be the first to welcome you to this web presentation, an introduction to LabVIEW object-oriented programming. I want to set your expectations appropriately and let you know that this will be an introductory presentation as the title implies. So I'm not going to assume that you have any prior knowledge of object-oriented programming, implementation in LabVIEW, or fundamentals leading into this presentation. We'll start with the basics. I will, however, assume that you have some LabVIEW knowledge. So we'll estimate your LabVIEW skill level at approximately the Certified LabVIEW Associate Developer rating of proficiency or higher. But just to let you know, if you're looking for more advanced content, this will be a simple presentation to really drive home the benefits and usage of the building blocks of object-oriented programming. But we do have advanced content out there. I'd like to point out one reference in particular. ni.com/largeapps is a great resource for any of the more complex information we have regarding LabVIEW and object-oriented programming. Today's presentation will begin with an introduction to object-oriented programming, but not as it applies to LabVIEW. We'll talk about the history of OOP, why it's important, when it should be used, and why it should be used. Then, as we introduce each fundamental object-oriented programming concept, we'll show you how it's implemented in LabVIEW. And lastly, I'll conclude the presentation by showing you how to get started using object-oriented programming in your own applications as soon as tomorrow. I find that in a lot of presentations, the concepts really make sense until you go off and attempt to actually implement on your own time. And so I'm going to help make that transition process easier. I think that this quote from Steve Steinberg of Wired is not only humorous, but also makes a really good point. There are those out there that believe that object-oriented programming should be the single approach you take when it comes to solving any programming challenge. My personal opinion differs from that. I think that object-oriented programming is a very valuable way of architecting and organizing your code, but I don't think it should be used as the single catch-all for every application. I think that object-oriented programming is a valuable tool that should be used as part of a larger toolbox at your disposal when it comes to solving challenges. There is, however, really good reason for the hype around object-oriented programming. The reason people like object-oriented code is that, in general, when used appropriately, object-oriented programs, object-oriented software is written with greater ease, performs with more stability, and also simplifies the maintenance on your part as the developer. Now, these are very bold claims, and I know you're probably thinking, that sounds amazing, but you're going to need to prove that to me. So that's what I intend to do with this presentation. As we introduce the fundamental concepts behind object-oriented programming, I'll relate them back to this exact slide and show you why each concept contributes to one or more of these benefits. Because many LabVIEW developers are domain experts and not necessarily classically trained in computer science, let's start with the basics. What is object-oriented programming? Very simply put, object-oriented programming is just a different approach to programming. It's a different way of architecting and going about creating a software application. The goal behind object-oriented programming is to make the software that you develop better represent and better model the way we actually think about and interact with objects or things in the real world. Object-oriented programming is not unique to LabVIEW. It's also not unique to any one particular language. There are many different languages out there that support object-oriented programming. Some support it natively, and some have been extended to include object-oriented support. You may have only recently begun hearing about OOP and its benefits, and that's because object-oriented programming has only become a dominant methodology in the last 20 or so years. The reality is that OOP dates back to the early 1960s when the artificial intelligence or robotics group at MIT realized that their applications, as robotics applications often do, began really growing out of control. The complexity of the software design, especially in their chosen language at the time, which was Lisp, really got out of hand, and they needed a better way to architect and organize their code that led to more manageability and better organization for these inevitable complex applications they were attempting to tackle. Code manageability is likely near and dear to you as well. No matter how hard you try and fight it, it's natural for software and hardware to grow in complexity over time. And when you combine that with the fact that the number of developers per team usually increases for a given application, and yet simultaneously the timeline that those developers have to release and update software decreases, a real challenge is produced, and that's why code manageability is of utmost concern. We did a survey in 2010 on our ni.com/largeapps website, and what we found is that the number of LabVIEW VIs in the average application is now, for the most part, between 250 and 1,000 total VIs. And a number of years ago, that number was far lower, and I think that speaks to the adoption and usage and applicability of LabVIEW in complex mission-critical applications. What we also found in that very same survey is that the number of developers per project in the typical LabVIEW project or LabVIEW application is also increasing. A handful of years ago it was one or just a few developers, and now it's not uncommon to find 5 or 10 developers per team. Each of those is a valid reason why code manageability is of utmost concern, but I think the most pressing of all the reasons is that as the traditional procedural program grows in size and therefore complexity, it naturally endangers data and therefore becomes very, very fragile, like a house of cards, where each change, modification, or addition could cause the whole program to come crashing down. And you may have experienced this before. If you've ever written an application where the same source of data, for example, a variable, is written to or read from in many different locations throughout that software, that's endangering data. That application is therefore fragile. So we're going to teach you about a methodology, object-oriented programming, that attempts to combat this. I used the term procedural program in the last slide, and I'd like to explain that concept a little bit further, as well as contrast it with the object-oriented approach. When the typical engineer who isn't classically trained in computer science sits down to attempt to write some software that tackles a particular challenge, the first thing they often do is attempt to model that software in terms of a procedural, step-by-step list of tasks that need to be solved, almost like a recipe, in order to successfully accomplish a given goal. Now, it's possible to organize this code by modularizing it into what we call subroutines, and in LabVIEW, of course, we call those sub-VIs. But the reality is that this code still dissociates data and behavior. Object-oriented programming is just a paradigm shift. It's a fundamentally different way of thinking about software design. The object-oriented approach focuses instead on data, and it views each independent compartmentalized piece of code as a series of interacting entities, almost like machines that communicate with one another. Each has a distinct set of responsibilities that it is designed to perform. And this way of compartmentalizing and organizing code actually unites data with its manipulators, and as we'll see in a couple slides, that actually becomes very, very powerful and very, very valuable when it comes to code manageability. So to summarize this section of the presentation, object-oriented programming really isn't anything magical. In fact, for any given object-oriented program, you could write a very clever task-based program or procedural program to accomplish the same set of challenges. Object-oriented programming is just a different way of architecting, organizing, and managing code. And so really what we like to say is that to begin implementing and using object-oriented programming, it simply requires that you begin to change your perspective and the way you look at your challenges and the way you architect your code. At this point, we're going to introduce the fundamental building blocks behind object-oriented programming. But before I do, I'd like to caution you that simply knowing and understanding the fundamental building blocks is not the same thing as being effective at object-oriented design. In fact, if you've ever tried to golf, you know exactly what this is all about. The simple basic concepts behind golf are very, very simple. You take a golf club and you try and hit a small white ball into a hole. However, if you've ever actually tried to put it together in practice, you know exactly how frustrating that can be. And the same thing holds true for object-oriented programming. We're really only going to introduce 5 concepts in this presentation, and they're all pretty easy when taken independently. However, that doesn't mean that you don't still need to challenge yourself and continue to practice the actual implementation and usage of those individual concepts. The first concept of 5 with the fundamental building blocks of object-oriented programming is a freebie. I guarantee you that you've used properties and methods before in LabVIEW. Properties, very simply put, are the characteristics of something, or in LabVIEW, of course, we like to think of those as the data. So, for example, if you were to describe me, the presenter, you might describe me by listing a series of descriptors like my height, my hair color, or my eye color. Methods, on the other hand, are the actual actions that a given entity can perform. So if we were to run with the very same example of a human, the things I might be able to do as a human are run, jump, swim, eat, sleep, and many, many more. In LabVIEW, properties are very simply just data. In fact, the properties behind LabVIEW objects are very simply a cluster or container of more fundamental primitive data types like numerics and strings. And just like you use clusters in your normal traditional LabVIEW programming, you're going to access the data within that cluster through the use of the bundle and unbundle functions. In LabVIEW, methods are very simply just VIs, or functions that you can call. So I told you that the building block number 1 is very, very easy, but let's do a quick check for understanding. If I were to ask you to think for a second about some properties of a DMM, you might come up with a list of things such as the vendor, the cost, the name of a DMM. If I were to ask you to think of the methods or actions that a DMM could perform, hopefully you're envisioning things like auto zero, reset, or measure. Once we understand properties and methods, we're ready to take into account classes versus objects. So we'll start with classes. Classes are very simply a definition of something. In fact, you can think of these like a template or a blueprint or a recipe for how something is actually architected or constructed. An object is the tangible existence of that class. So these are the things that you actually use in code and manipulate, and they are the instantiations of something that a class has defined. When you're using LabVIEW classes and objects, you're going to be actually interacting with the LabVIEW project dialog. In fact, in the image you see here on the slide, there's a few classes defined in this project. At the bottom of the project, we have something called the shape class, and then we also have some more specific classes, one called circle and one called square. Now the square class has actually been expanded, and you can see that it has a control, and we'll call that the class private data. That's where the actual properties exist, that cluster we referenced earlier. And this individual square class also has one single method called draw, and that's an action that it can perform when used in code. After you've actually created and organized your LabVIEW classes in the LabVIEW project, and you drag an individual LabVIEW class onto the block diagram, you're creating an instance of that class for use in your code, and we call that an object. As the object travels around your code on the wire, what you're doing is you're actually passing around a bundled set of data, of course, the class private data we alluded to earlier, as well as the functions that help you manipulate that data. And of course, since a class is the definition of an object, the data type of the wire on which an object flows is its class. Now there are a lot of really neat things about objects and classes when used in LabVIEW code. For example, the wire appearance can be customized, so you can actually really differentiate and highlight the use of object-oriented programming in your LabVIEW application. Let's actually open up the LabVIEW environment now and show you how you create some brand new classes, properties, and methods in LabVIEW. Okay, in our first demo we're going to create our very first set of LabVIEW classes and use them ultimately in objects in the very next demo. So as I mentioned before, LabVIEW objects and classes are actually created and organized and managed through the use of the LabVIEW project window. So I've already created a LabVIEW project here. All it has is a very simple main VI. I've pre-populated that with a few things. We'll get to that in a second. But right now there are no existing classes. So to create a class, simply right-click on my computer and choose New Class. And what we're going to do is we're going to create a little application that draws a few shapes in a 2D picture control. So the very first thing we'll define is a higher level abstract or generic shape class. So we'll provide it a name called shape. And now you'll see the an
addition of the shape class in our LabVIEW project window. Notice by default the shape class has the shape.ctl file. If we were to actually double click on this, this is the class private data, that cluster we sort of alluded to in the slides, that every single LabVIEW class has. So for our shape, we're going to keep it simple. The only since a shape could be really anything, it could be a square, it could be a circle, it could be a triangle, the only private data or property we're going to use is just the color. So I'm going to right click and I'm going to choose numeric, and the framed color box should be fine for that. And so we'll just rename this to color. And so now I'll press Control S to save the class private data. And the first thing I'm going to need to do, of course, is to save the class. And so we'll save this in the shape folder. And now let's go ahead and add a method to this particular class. So right now we've already configured the property, which is a color. We're going to add a method. So I'm going to right click on the shape class, and I'm going to choose new. And what I'm actually going to choose is new VI from dynamic dispatch template, and that's because later on we're going to be actually overriding this particular method that we're creating with some subclasses. So this is going to be a method. Notice that it has already pre-configured some inputs and outputs. If I press Control E to access the block diagram, you'll see that the class comes in and is also passed out, so we can access the information contained within this class as we're using it on the block diagram here. This particular method is going to actually be the method that draws our shape. The problem is, since we're dealing with a generic shape class at this point in time, we don't know what to draw. So really the only thing we can do is provide a contract with the outside world. We know that the shape class is ultimately going to output a 2D picture. We just don't know what's going to be on that 2D picture at this time. So I'll switch back to the front panel and use Quick Drop to find the 2D picture control. And so the only thing I'll do here is move this to the right hand side. Again, I can't really populate this particular method because we don't know what shape to draw in this case, but that's okay. As long as I connect this to the connector pane, we should be able to override this with a more specific implementation a little bit later. So I'm going to choose to save this particular method, and I'll call it draw. I mentioned we're going to be overriding this draw method, and so why don't we go ahead and create a few subclasses at this point in time so that we can override them a little bit later. So I'm going to right click and choose new class. Let's go ahead and create two different classes. One we'll call circle, and again this is going to have its own class private data. So why don't I save this by pressing Control S. And we'll create one additional class here. So right click and choose new class, and we'll call this one square to keep it simple. And so I will additionally save this particular class in the square folder.
Now that we're done with the second fundamental building block, let's do a quick check for understanding. So pop quiz. Of this cookie cutter and cookies, which is the class and which represents the objects? Well, hopefully you were thinking that the cookie cutter itself is the class or the definition, blueprint, and the cookies themselves are the actual instances or objects. For you Star Wars fans out there, how about this blueprint and R2-D2? Which one is the class, which one is the object? You guessed it. The blueprint itself is the class. It represents the definition of R2-D2, and the actual image of R2-D2 here is the object. And one last quiz. We have a water drop and we have an actual water molecule, or H2O. Which one's the class and which one is the object? Well, hopefully you were thinking that the actual instance of water, the droplet itself, is the object, and the definition of that molecule is its class. The third building block of object-oriented programming is called encapsulation. As we mentioned earlier, with the typical procedural program, there is not a formalized connection between data and the code that can possibly manipulate that data, whether it be reading to access or writing. So for an example, if you abstract LabVIEW away from the equation and just think of a traditional C application, you can organize units of code into what we call functions. You can organize units of data into what we call structures. Functions can operate on different types of structures, and for a given structure, more than one function can actually access and operate on that structure. So as you can see, this naturally endangers data because there's lots of different places that data could be modified, and that creates a problem as applications grow in complexity. Encapsulation is the idea of taking data and the methods or functions that allow the outside world to interact with that data and uniting them into one unbreakable bond. We call that structure an object. So an object is very simply the unity of data and the methods for manipulating that data. This may seem like a little bit of extra overhead to you, but there's actually a lot of benefits that you gain from encapsulation. So if you think of the rest of your application as the outside world, your main application is going to view a given object with the encapsulated data and methods as a black box. Here's what that means. The outside world, when it needs to manipulate the data within an object, can never do so directly. It must always interact first with the methods that you as the developer have predefined for interacting with that data or manipulating that data. The benefit here, of course, is that an object can store data in its most convenient fashion, and then it can serve up that data to the rest of the outside world or the rest of the application in the way most convenient for that application. So there's a translation that can occur with that data, and that happens in the form of the method that you use to interact with that data. And that also gives yet another benefit, which is that there's a single choke point that you as the developer need to go to in order to fix bugs or make enhancements to your application. And that's the individual methods that we call accessors that allow the outside world to interact with the data within an object. Let's do a quick tangible example here to demonstrate the benefits of encapsulation. Let's pretend for a moment that I work as part of a development team. We don't have to focus on the details of what the application I'm working on actually entails. Just know that I'm going to be passed some sort of data from a code module created by one of my colleagues. My job is to manipulate that data with a set of defined IP, and then I need to provide the results of that manipulation to yet another colleague. Let's pretend for a moment that the data I'm provided by my colleague is actually representing a circle. And the way in which we're representing that circle is through the use of color and radius. So I make some assumptions about the data I'm going to get, and I actually go about writing my IP, which of course does some very simple manipulation regarding the radius of that circle, and then my code actually outputs the results of those calculations, things like the area or the circumference of the circle. I output that information to the next developer in the chain. Well, there's a problem here, and that's in the assumption that I made. Let's say for a moment that though I assumed the radius would be given to me in inches, I'm working as part of a global development team, and since centimeters are the standard unit of length in a lot of different countries outside of the USA, the global developer that I'm working with is actually providing me that data in the form of centimeters. The issue is that I've already written a lot of IP in order to access that radius value in inches, and of course my IP is dependent upon that value being in inches. So if I were to try and accommodate this change, I would actually have a problem. I'd have some work to do. The good news is that I'm a bright LabVIEW developer, and I know that the conversion between centimeters to inches can be done pretty simply. I can build it into a sub-VI, and that sub-VI can be reusable across my application. Not too big a deal with this very simple example, but imagine if this was an actual real-world complex set of code where I would now have to touch many different parts of the application in order to fix this bug that was introduced thanks to my assumption. That might actually cause a lot of headache, and that's where the concept of code manageability comes in. Let's take a look at what would have happened had I used object-oriented programming as my approach from the start. I still would have made my false assumption that I would be provided the radius value in inches. I would have bundled that, however, into an actual class and encapsulated that data and methods for accessing that data in the form of a circle class. And then, of course, I would call the data accessor method, which is called getRadius in the form of a VI, in order to access the actual radius value provided to me by my colleague. I could then perform my IP and pass the results downstream. Now, of course, I did make that false assumption, which means we'll need to go back and make the update and change radius from inches to centimeters, which means I still have to be responsible for a conversion back to inches, since that's what my intellectual property depends upon. However, instead of having to go write that sub-VI and touch many different places in my code, I know exactly where the rest of my application goes in order to access this radius value, and that is to the accessor method that I've defined. So I can use that sub-VI one single time, make my conversion, and the rest of my application can actually stay the same, and that's very important, and that's a benefit of encapsulation. So if we were to apply the abstract concepts of encapsulation to the real world, and ask you to think about the benefits of encapsulation as it applies to automotive engine technology and the way in which you as a driver interact with that technology. The way in which you might explain it is that automotive technology in the form of engines is very frequently changing. It's also very complex, and you can think of that as the data that a given object stores. However, the outside world, which is you, the driver of the automobile, doesn't need to worry about the way in which the engine is actually architected and what goes on under the hood. You just need to know that there's a standardized, well-defined way of interacting with that engine, and that's through the use of the cockpit, which contains a steering wheel, pedals, and a shifter. As automotive technology advances or changes, it can continue to be stored or used exactly as the automotive engineers see fit, and as long as they don't make too many drastic changes to the cockpit of the automobile, you should be able to get into any vehicle and drive the car even if you've never driven it before. I mentioned in the beginning of the presentation that I was going to relate the abstract fundamental concepts of object-oriented programming back to the three bold claims that I made about object-oriented applications. Encapsulated code is written with greater ease because each component that uses data, as we talked about, can store that data in its most convenient form. Additionally, object-oriented code is more stable because if you need to make an update, for example, to your code or fix a bug, there's less about your overall application that needs to change to accommodate those modifications. And lastly, of course, as we've sort of already alluded to, maintenance is also simplified because if you need to fix bugs or introduce new features, less things need to change about the application. The fourth of five fundamental building blocks of object-oriented programming is called inheritance. And you can think of inheritance the exact same way you think of inheritance as you would apply that term to genealogy. The idea is that classes, as you define them in the LabVIEW project, are organized hierarchically, which means that just like parents can pass on traits to their children, classes can pass on properties and methods to child classes, which means you can define very vague, abstract classes as the starting point for more specific classes that will be implemented down the line. Here's an example of that in action. Imagine that we have an abstract class called 2D shape, and that's a very generic term. 2D shape could mean a lot of things. In general, there's a couple different types of 2D shapes. You can say very abstractly that there's a polygon, and of course that there's a circle. And within polygon, you could dive even further and say quadrilateral, pentagon, hexagon, depending on the number of sides, and you can continue to traverse down the hierarchy even further. Well, let's imagine that at the 2D shape level we implement a couple of methods. One is called draw and one is called getColor. Now there's sort of a problem here in that draw is very vague, and it's really difficult to define the way a 2D shape is actually drawn, because a 2D shape could be a lot of different things. But because of inheritance and because each of these child classes inherits from 2D shape, each one is going to have access to a draw method and a getColor method. And at each lower level of the hierarchy in the child classes, when appropriate, we could implement the draw method specific to that child class. If we were to, for example, define a brand new method at the level of the quadrilateral, pentagon, and hexagon, and we call that method countSides, which of course makes sense at this level of the hierarchy since these shapes have straight edges, and don't make sense at the circle level, for example, since the circle has 0 straight edges, the count sides method would then be inherited by all child classes as well. Now this is an extremely valuable technique. Inheritance depth is unlimited, so you can organize your hierarchy however you see fit. And the really cool part is that since child classes already know how to do everything their parents can do, they inherit a lot of pre-existing functionality, perhaps that has already been proven and tested. Additionally, child classes can override parent functionality, which means that a parent can define a contract with the outside world as to how a given set of data is to be interacted with, but yet each individual child class can implement a specific version of that interaction as they see fit. After you've defined classes in the LabVIEW project, you can actually dictate a hierarchy of those classes and therefore define inheritance by right-clicking on the individual class, choosing Properties from the right-click context menu, and then selecting Inheritance. Now I mentioned that inheritance depth is unlimited, and therefore you could come up with some pretty large class hierarchies. And of course LabVIEW includes some productivity enhancements here to make your life a lot easier. If you right-click on any class in the LabVIEW project, you can choose View Class Hierarchy, Show Class Hierarchy rather, and you'll get a really neat interactive diagram that allows you to expand and contract individual levels of the hierarchy as needed in order to really understand the way in which each individual class relates to other classes. Since child classes already know how to do everything that their parents can do, some really amazing things can begin to happen. And you see that as an example here on the LabVIEW block diagram. We've defined a couple of classes, one generic shape and a circle that inherits from shape. We use an object, shape object on the block diagram, which travels along its own wire and is then cast to a circle. It travels along a circle wire for a while, and is then cast back and represented by a shape. Now this can happen of course in LabVIEW without any loss of data, which actually differentiates LabVIEW from a lot of the other languages out there that use an object-oriented approach. In order to access these functions called toMoreSpecificClass and toMoreGenericClass, you may have seen these before. They're located on the cluster, class, and variant palette on the block diagram. Our pop quiz for inheritance defines the class hierarchy here that you see on the slide. Imagine we have a generic mammal, and inheriting from mammal is a canine and a feline. Each of these three classes has their own individual methods that they've defined, as well as a single property. So if we imagine that I've got an object of the canine class and I call that object my dog, which of the following makes no sense? Well, if we were to try and call getEyeColor, the method of my dog, just because getEyeColor isn't explicitly defined in the canine class doesn't mean that my dog can't use that method, because of course it inherits that method from the mammal class, its parent. If we were to try and call the clean fur method of my dog, that wouldn't make any sense, because the feline class defines clean fur, and canine does not have an implementation of clean fur, nor does it inherit clean fur from the feline class, as they are siblings. The benefits of inherited code are also vast, just like that of encapsulated code. It's written with greater ease because, quite simply, you can write code once in a parent class, and child classes can inherit that implementation from their parents, which means if code is already written or proven, it can very simply be reused by child classes. It's performed more stably because if that code has been tested, and if parent code has been tested and a child class simply reuses that parent code, you shouldn't need to retest that. And of course it simplifies maintenance because you can write code one single time and sort of abstract the more common or more generic functionality to the parent classes, and that functionality can then be used in the child class simply because of inheritance. Perhaps the most amazing and powerful concept in object-oriented programming, and in fact the fifth of 5 building blocks, is dynamic dispatch, which builds upon the benefits of inheritance. The idea behind dynamic dispatching is that objects that are built from classes in a class hierarchy can actually determine on the fly which version of a method to call, a child version or a parent version. And you can sort of think of this as dynamic polymorphism. And you've probably used polymorphism before, for example, if you've ever used the DACMX API. The DACMX read VI, there are many different implementations of that individual VI depending on the type of measurement you're trying to do. The difference is that you have to choose which version of the DACMX read VI you call at edit time. However, dynamic dispatching gives you the very same benefit, but at runtime. And again, this all stems from the fact that a parent class can define an entry point with the outside world, like a contract, that children can fulfill. Now, not just any method or not just any VI is a dynamic dispatch VI. There are 5 things that must be true for a dynamic dispatch VI to be in place. First and foremost, that VI must be inside of a class, of course. It must be a method of a class, and that class has to be part of an inheritance hierarchy. If you are attempting to create a dynamic dispatch VI within child and parent classes, the overriding or child VIs must have the very same name and identical connector panes, save for the upper left and upper right terminals, which of course represent the object coming in and going out of the method. And lastly, those upper left and upper right terminals must be explicitly designated as dynamic dispatch terminals. In the demo I'm about to do, I'm going to show you how to very, very easily make sure that all 5 of these prerequisites have already been taken care of so that you don't even need to worry about them. So let's continue the simple LabVIEW example that we were building upon earlier and actually implement inheritance and dynamic dispatching within this application.
Okay, so in our first demo we created a few classes and we added an additional property and an abstract method as well. So the shape class is our parent class. It has 2 subclasses that we've defined but not yet defined inheritance. And within the shape class, remember that we have created a color property. And we've also populated a draw VI. It's pretty generic at this point. It doesn't do anything other than the fact that we know that this draw VI is going to be overridden, and it's going to output the shape of the image of the shape that we're trying to draw. So the first thing that we're going to do is we know that we're going to want to get access to the color property within our application, within some of these other classes, particularly in the method, draw method that we're going to wind up overriding. So what I'm going to do is right click on the shape class and choose new VI for data member access. This is a pretty neat LabVIEW productivity enhancement. It allows me to actually select one of the properties that I've defined. In this case there's only one, color. And I can choose whether I want a VI that reads information from that property, writes, or both reads and writes. So when I actually select create, LabVIEW is going to script behind the scenes the VI necessary to unbundle that property or bundle that property for reading and writing respectively. So in just 1 second here I should have access to those VIs. So these were programmatically created by LabVIEW. So if I take a look at the block diagram, this is the right color VI. LabVIEW created all this code for me. Notice we're just bundling up the whatever color comes in and saving it to the class private data. So I can just go ahead and save as is. We'll keep it called right color, that's fine. And I'll save the read color VI, which is almost identical other than the fact that it simply unbundles the color property. So I'll save this as well. Now I can define inheritance. So we've got this abstract shape class, and what I'm going to do is tell LabVIEW that circle and square inherit from shape. And recall that to do that I'm going to right click on the class, choose properties, select inheritance, and I want to change the inheritance of this particular class. So the circle class right now inherits from a generic LabVIEW definition. We actually want to select shape and choose inherit from selected. We'll do the same thing for the square class. Select inheritance, change inheritance, and we also want square to inherit from shape. Now what this will allow us to do is access both the color property as well as any of the methods that have been defined as potentially overridable from within these child classes. So let's go ahead and, for example, override the draw method for the circle class. So I'll choose right click and choose new VI for override, and this will populate a dialog with all of the potential methods from any parent class that we can override. So we're going to override the draw method. So the question now becomes, what does the draw method look like for a circle? So this is up to us to actually populate the block diagram of this code. LabVIEW automatically adds in a call to the parent's version of draw, which we're not even going to need in this particular example. Really what we're going to want to do is two things. First and foremost, we need to figure out what color this circle is supposed to be, and then after that we need to actually draw the circle. So the first thing I'll do is take the read color method from the parent, drag and drop it onto our child class implementation of draw here, and this is going to take a shape input. Notice it's a shape input, but I'm passing in a circle, and that's okay because circle is a child of shape, so there's no problem there. Now let's go ahead and access the draw circle function. That's within the graphics and sound palette on the block diagram. I'll go ahead and show the label so we know exactly what that's doing. This takes a couple of different inputs. One of them is a picture control. We've also got a radius, so we'll specify just a default value of 10, something simple. We'll need to provide a center pixel. Again, keeping it simple, we'll do 30, 30. We're going to have to choose whether or not to fill this circle in. I'll go ahead and choose true. We have to provide a color. That we have access to actually from the read color VI. We already got that, so I'll pass that in. And then we'll definitely want to take the resulting circle and pass it to the shape output. So I'll go ahead and clean that up. So in this case it looks like we've completed all the work we need to in order to draw a circle appropriately. We pass in some parameters defining the size and color of the circle we want to draw, and we pass the output to the 2D picture control. So I'll choose to save this. I can override my existing version here. And we're going to do this one more time, and this particular instance is going to be for the square. So I'll right click on square, choose new, VI for override. We're overriding the draw method of the shape class. So what does it look like to draw a square? Well, very similarly, LabVIEW pre-populates this with a call to the parent version, which we don't need. We are still going to read the color of the square. I'll do this a little quicker here. I'm going to use quick drop to access the draw rectangle VI. So this is going to take a few things. It's going to take pixel values representing the, I believe it's the upper left-hand coordinate and the lower right-hand coordinate for the square. And then choose whether or not to fill this in. We'll choose true. We need to provide a color, which we can get access to from the read color VI, and then the output of this method is going, this particular VI is going to be, of course, the shape that we're drawing. Looks like I have an issue here. Oh, we need to pass out the square. Okay, so now I'll go ahead and save this VI. It doesn't look very good, but that's okay. It gets the point across. So now we've just populated the draw method, which we've overridden in two different child classes of shape. So now it's time to actually take a look at our main VI and implement this code here. So I mentioned earlier that I'd pre-populated this VI. I have a 2D picture control on the front panel, and on the block diagram I've set up a little application here that simply takes in two colors, ultimately outputs a picture control, and it does this in a loop. There's a wait in between of 2 seconds so that we can actually see one shape drawn after another. So let's go ahead and drag a circle and a square onto our block diagram. I'll choose to show the labels, and we're going to go ahead and build this into an array. Now, one of the interesting things about working with classes and objects here is that circle and square technically are two different data types, but since they actually inherit from the same parent, which is shape, it's possible to bundle them into an array. You normally couldn't do that with LabVIEW primitive data types, such as taking a numeric value and a string value and trying to build them into an array. That wouldn't work. That would cause some sort of an issue at compile time. So what I'll do now, the first thing we're going to need to do is for each of these objects that we're using on the block diagram, we're going to want to populate the color, which is coming in the form of a constant, and then we're going to want to actually draw the shape. So we're going to use the right color method. This is the parent version of right color. We don't have an overridden version of this, but that's okay because circle and square are both shapes, so it's possible to use this. And then after that, we're going to want to draw the shape. So I'm going to, rather than using the circle implementation of draw or the square implementation of draw, we're going to use the parent's version because at runtime here, the first iteration of this loop will have a circle, the second iteration will have a square, and so we need to use the more abstract version of this particular method. So when I go to my block diagram now, or I'm sorry, my front panel now, and I run this application, the first thing I should see is a circle, and after 2 seconds I have a square. So this is a pretty neat overview of very simply creating a couple of classes. We're defining an inheritance hierarchy, adding some properties and methods to those classes, and then in this particular application we are nicely showing off the power of dynamic dispatching, since at runtime this set color VI, right color VI, sorry, and the draw method are actually being dynamically dispatched. The draw method in particular is being dynamically dispatched based upon what comes in at runtime. And you can actually prove that and demonstrate that out a little further. If I were to double click on this draw VI to try and take a look at the source code, I'll pose a question to you. Which version am I going to see? Am I going to see the version that we defined at the shape level, the circle level, or the square level? Well, actually that's a little bit of a trick question because there are really 3 different versions of draw, and the version that we access depends on exactly what comes in at runtime, what type of object comes in at runtime. So when I double click on draw, I'm actually going to get a dialog box where LabVIEW asks me to choose the implementation. So let's just go ahead and take a look at square, and if you recall, this is what it looked like when we chose to draw a square. So it's a nice demonstration of the concepts we've learned thus far in the presentation.
So to check for understanding with our final building block, dynamic dispatching, we're going to do a quick quiz that regards the actual inheritance hierarchy we looked at earlier in the slides. The question is, if we were to try and call the draw method at each one of these individual levels of this class hierarchy, what would we get as an output of that draw method? Well, let's start at the top with 2D shape. It's really difficult to draw a 2D shape because you almost certainly have to ask yourself, what 2D shape? A 2D shape could be many different things. So really it's difficult to implement the specifics of the draw method at the 2D shape level of the hierarchy. Very similarly with polygon, there are many different types of polygons, so you don't really know what the output of the draw method for the polygon level is going to be either. However, if I asked you to draw a circle, you could undoubtedly and definitively draw me a circle that you know in fact to be a circle. So there would be a very specific output for the draw method of the circle class. With quadrilateral, we continue the trend that we're not exactly sure what the output of draw will look like, but with pentagon and hexagon, since we know each of those contains 5 and 6 sides respectively, we should be able to have a definitive output for that method. And with rectangle, of course, we should be able to definitively draw a rectangle, and the same holds true for kite and rhombus. So you can see here how we can actually define a method at the parent level and then actually implement that method when it makes sense lower in the class hierarchy. And since there is inheritance at play, dynamic dispatching can actually take place where the actual version of the draw method that gets called can happen dynamically, can be decided dynamically at runtime. While I can't make the claim that dynamically dispatched code actually performs with greater stability, I can outright state that it is written with greater ease and it simplifies maintenance. Since we can define promises or contracts at the parent level without having to care about the individual details of implementation at the child level, just knowing that the child will implement that when defined, the code can actually be written with greater ease. And also, with regard to maintenance, new features can be introduced to extend your existing application simply by creating a new child class and ensuring that that child class inherits from some sort of a parent and follows all the promises or contracts made and defined by that parent. Now, the demos in the previous section were intentionally simple so that you could focus on the concepts and the building blocks behind object-oriented programming, see how they're used in LabVIEW, and begin to see their benefit. But let's step up a level in complexity with a more realistic application. So let's pretend in the upcoming demo that we've been tasked by a brand new coffee company called Starbuzz to design a cash register system. Starbuzz is a new food cart here in the Austin area that only sells just a few drinks, coffee drinks in a few different sizes, but they've asked us to design this point of sale system with growth and scalability in mind. Their popularity is booming, their business is booming, and they think that they're going to come up with a number of new drinks and want to make some changes in the near future.
Let's take a look at a little bit more complex example of object-oriented programming, just one step up from the shapes demo we've done thus far. As I kind of mentioned, setting the stage, that this little fake application here is actually a point of sale or a cash register system for a fake coffee shop. I've actually written this demo 3 different times. The first time I wrote this demo, it was without object-oriented programming, and I've written 2 versions with object-oriented programming to show you the benefits, demonstrate the benefits in sort of a real-world scenario of using OOP for an application like this. So let's first take a look at the non-object-oriented programming version. As you can see, the front panel looks like a cash register. It's got a couple buttons to select the brew of coffee and the size of the coffee, and then you can add additional drinks to the order. Let's take a look at the code so you can see what's actually going on behind the scenes. Very simple here. You should recognize this is just an event structure which is contained within a while loop. I figured when I wrote this code I needed to have some sort of way of representing a drink and then also an order, which is multiple drinks. So my first inclination was that a drink is going to be a cluster, and it's going to depend on the brew and the actual size of the brew, and that the order, which is a series of drinks, is going to be an array of drinks. So that's what I wound up creating here for this first iteration. You can see that the event structure reacts depending on the brew that was selected. We're simply changing the brew of the existing item in the array. If you change size, we're changing the size of the existing item in the array. And then the last thing I'll point out is the total button. What happens with the total button is we actually take the array, we iterate through every item in the array or every drink in the array. We figure out what size it is, and based on the size, we populate the cost. So let's just give this a run real quick, and I'll show you how it works. Let's first add a grande mild drink. We'll add it to order, and then we'll do a tall bold drink. And when we total it up, that should be the summation of our order. So it looks like it functions, theoretically. The problem is, as soon as you try and scale this application or make changes to this application, you may run into problems. And I'll give you an example. Let's say that the Starbuzz company approaches me and says, hey, we've decided to change the cost of our venti drink. So we actually want you to update that. Well, I might go in here to my code and take a look. I seem to recall that in the total, in the event case for reacting to the button press of total, that's where I do the population of the actual cost of a venti. So let's say it goes from $2.99 to $3.99. Theoretically, this should be fine. So when I actually go to back to my front panel and run this code one more time, let's just test this out real quick. We'll take a venti mild. Wait a minute, the cash register is displaying $2.99 and not $3.99. When I total this up, though, $3.99 is calculated. And this is a prime example of data, the same type of data being accessed in multiple different places within my application. So you may have applications that experience this type of thing already. Only your data might be, for example, measurement data, or it might be instrument handles or something like that. And the reason this, of course, that this is happening is that I calculate the total cost of an order in this particular event case, but actually when I select the size, I'm using a different set of data, similar set of data to represent the same thing. In other words, the data and the places in code that modify that data are disconnected, and we mentioned that was one of the fundamental things that object-oriented programming sought to overcome. So I'm going to close this version of the code and open up the object-oriented version. You're going to notice The front panel, of course, is identical, but let's take a look at the block diagram. This is going to look extremely similar. Still, we've architected it the same way in the form of an event structure with a while loop. In fact, each one of these cases looks nearly identical. The biggest difference here is that instead of representing a drink in the form of a cluster, and an order in the form of an array of clusters, we're populating a drink class, and that drink class uses as its private data the type of brew and the size of the brew, and that then can be created and added to an array. And the benefit there is that it allows me to create methods for obtaining the description or getting the cost, and that's one single point in my application, one single point in code that I can point to and say that is exactly where the cost is actually changed. So let's run this first without changing the cost of a venti. We'll add a mild venti. $2.99 was our original price. If we total it up, it indicates a total of $2.99. If I were to attempt to make a change, I know without a doubt that the getCost method is the exact place where the cost of a venti is calculated. This, of course, is a dynamic dispatch VI. So I'll open up the venti version, and here is the exact point in code where $2.99 needs to be changed to $3.99. So if I save this now, go back to my front panel and give this a run, now whenever I select a mild venti, the cash register indicates $3.99, and when I choose to total it up, $3.99 is the exact same thing that's displayed on the cash register. So this is a really nice example of data being endangered in a normal traditional application and how that's overcome with object orientation. Let's take a look at one more version of this demo. The version of this demo we're going to show off now is again very similar. The only difference is that I kind of want to give you a little teaser of the fact that simply knowing the basic fundamentals of object-oriented programming is it really only gets you so far. What you want to do is now that you know the fundamentals, seek to further your education and learn some of the common object-oriented design patterns. What we've done here is we've extended the Starbuzz demo in order to allow us to select a brew, select a size, but then add modifiers like milk, whipped cream, or mocha and soy. In the code, almost everything is identical. The only difference is that we have a place where we're reacting to someone selecting a modifier or a condiment. And what we're doing here, if you can tell, we're taking our drink and we're actually populating this drink using a method called setElegantDrink to, if you will, effectively decorate each drink with a series of condiments. So you can decorate your class with another class and continue to do that. If I wanted to add double whip or whip and mocha, for example. And this is, as the name sort of implies, this particular object-oriented design pattern is called the decorator pattern. So if I were to take a look at how this code actually executes, let's choose a grande mild brew and we'll add some milk to that. And then an additional drink we'll add to the order is a bold venti with soy and mocha, just as an example. So that's how the decorator pattern works, and hopefully that's a good encouragement for you to take a look at some of the common object-oriented design patterns and really take your knowledge of object orientation from the fundamental level to the advanced level.
Hopefully you've seen the benefits of object-oriented programming and you're excited to begin using OOP in your own applications. So in order for you to take the plunge and begin using object-oriented programming, I encourage you first and foremost to start by simply approaching application challenges a little bit differently and reframing the way you think about an application. Instead of using the traditional procedural way of thinking and looking at things, try and look at it with an object-oriented design in mind. One of the things you can do is look in your existing applications and find what I like to call the clustersaurus. And that's usually a cluster that contains a lot of different data types that you pass around an application, for example, a state machine. If that cluster contains a lot of disparate data types that really aren't cohesive and are accessed from a lot of different places, that's often a very good place to start implementing object-oriented programming in your application. Additionally, if you have any type defs that you've defined as part of entities within a LabVIEW project, you can right-click on that type def and choose to convert that type def to class, and LabVIEW will actually take care of creating a class from that type def automatically, which is pretty neat. As usual in LabVIEW, there's a ton of examples in object-oriented programming, so take a look in the example finder for a lot of good examples. You can use them as the starting point for your code. And in order to actually take the fundamental concepts that we just learned about and begin to scale them with real-world application design, I encourage you to navigate to the URL you see here on the screen, which details the use of OOP in LabVIEW as it pertains to proven computer science design patterns that have been out there for decades. In conclusion, every time you sit down to write software, know that software traditionally isn't written, it's rewritten. In other words, you need to plan for the future, and whether you're sitting down to write a very complex application or you think your application may grow in the future, just know that code manageability, especially when it comes to scalability of code, is something you should be thinking of now. It's easier to think of now and plan for now than attempting to go back and update things in the future. While object-oriented programming isn't applicable and important to use for every single application challenge out there, there are a lot of places where OOP will really simplify your lives. We saw some basic demos in LabVIEW and we learned the fundamental building blocks of object-oriented programming, but the key takeaways to the presentation are that object-oriented programming, when architected and designed appropriately, in general is written with greater ease, performs with much more stability, and simplifies maintenance on the part of the software developer. Thank you very much for attending this presentation, and good luck implementing OOP in your own applications.